Hello class. As promised, we're going to talk a little bit more about gases. First, we'll review a few concepts that we already covered and look at some ALEKS problems. And then we'll move on to integrating a lot of the things that we learned into some problems that we'll solve. Okay, so when we think about gases, one of the first things we touched on was kinetic energy. Now the formula for kinetic energy, and now this is not just for gases, this is for anything. Kinetic energy, or the energy of motion, is 1/2 m, which is mass, v, which is velocity, squared. And so if you're throwing a ball, throwing a rock, and dropping something off the roof, right, these are the kind of problems you see if you take Physics 1, kinetic energy equals 1/2 mv squared. So we say Ke equals 1/2 mv squared. Now when we're talking about a ball or a rock, m is in a mass, that's in grams or in kilograms, and velocity is in something like meters per second. Now in chemistry, we don't really think about our atoms and our molecules individually in terms of grams or kilograms. Right? So we don't really use the kinetic energy formula to solve for kinetic energy of one single oxygen molecule. But we use this formula to think about the energy of molecules. And so we have 1/2 mass times velocity squared, and in chemistry, velocity is not typically written as v, but u. Right? U is what's called the root mean square speed. Generally, the term that we'll use instead of root mean square speed, though, is just the average speed. Right? So the average speed, the average kinetic energy of a molecule equals 1/2 mu squared, where mass is the mass of the molecule and u is the root mean square speed of the molecules in the gas. Because the molecules in an example of gas are all moving at different speeds, but they have an average speed. And actually, there's a relationship between the speed of the molecules and the temperature. So as the temperature goes up, u, the root mean square speed, also goes up. And so therefore, as the temperature goes up, what else goes up? The kinetic energy also goes up. And actually, this is key, because for any gas molecule, for any sample of gas, the average kinetic energy depends only on the temperature. The higher the temperature, the higher the Ke. The lower the temperature, the lower the Ke. Okay, but I just told you something that may make you say, huh? Because I told you as temperature goes up, u also goes up. So where does speed come into this? Well, for a sample of gas, any particular gas, at a given temperature, right, because of this, average Ke depends only on temperature. At a given temperature, we talked about this, mass and u squared are inversely related. Big molecules, higher mass, have lower speed. So high m, low u, or low u squared, low m, high u squared. And so we can have, or we have another relationship that says the speed of the molecules is equal to the square root of 3RT over the molecular weight of, or the mass, you could think about that as the mass of an atom. And so what does that mean? That means gases with high molecular weight, let's say SF6, right? That has a very big, it has 1 sulfur, 6 fluorines, it's very big. It has a high molecular weight. Because the molecular weight is in the denominator, that means it will have a very low speed. Whereas something like hydrogen or helium, right, these are very light molecules, they have a low molecular weight, and so because they have a low molecular weight, they will have a high speed. And so the speed and the molecular weight cancel out. And when we're thinking about kinetic energy, the only thing that matters, remember this, the only thing that matters is the temperature. Okay, so let's do our first Alex problem here. It says 5 samples of helium gas are described in the table below. Rank the samples in order of increasing average kinetic energy of their atoms. So 1 is the lowest, 2 is the next, and then all the way up to 5, which is the highest. Now, what did I just tell you? I just told you kinetic energy of gas molecules depends only on what? Only on temperature. So there's a whole bunch of information here that you can ignore, right? When you see average kinetic energy, average molecular kinetic energy, average kinetic energy, you're going to think temperature. And therefore, do we care about the amount, the moles? No. Do we care about the pressure? No. We only care about the temperature. And so higher T equals higher KE. So we're going to rank them from lowest energy to highest energy, which means we're going to rank them from lowest temperature to highest temperature. Now the only thing we need to pay attention to here is the negative sign. So because all these numbers are negative, the bigger number, the bigger negative is a lower temperature. So the lowest temperature is minus 84, that's going to be 1, and then minus 68, and then minus 54, and minus 49. This question asks how the average molecular speed scales with temperature and molar mass. Average molecular speed. This is different from the last slide. The last slide asked about average kinetic energy. Average kinetic energy, as we saw in the last slide, only depends on temperature, but speed scales with both temperature and molar mass. The formula is U, right? The root mean square speed, or the average speed, equals the square root of 3 times R, the gas constant, times T, the temperature in Kelvin, over molecular weight. So what you see here is T, temperature, and molecular weight, or molar mass, temperature and molar mass. Now don't get frightened by the square root sign. The square root sign makes a difference when we're doing calculations, but when we're thinking about whether things get bigger or smaller, the square root sign doesn't really make a difference. If something's in the numerator, it will make U, and it gets bigger, then U will get bigger. If something's in the denominator, and it gets bigger, then U will get smaller. Okay, so let's look at molecular weight. And we have two, and so in this question, we're asked to rank the samples of gas, right? in order of increasing average speed, so the slowest to the fastest. And we have two atoms, or two elements, argon and krypton. And these two elements obviously have different molar masses. And so the molar mass of argon is, I knew it, but I forgot it, I'm looking it up now, is 39.9 AMU, or grams per mole, right? 39.9 grams per mole. And krypton is bigger than that. It's, let's see, 83.8. 83.8 grams per mole. So if they're at the same temperature, then the one with the bigger molecular weight, or the bigger molar mass, moves slower. All right, so let's break this down. Fast molecules have high temperature, right? Lots of energy. Temperature scales with energy, so high temperature and low molecular weight, right? So if you have small gas molecules like helium or hydrogen, they'll be zipping around real fast. Then if something's moving slow, it's going to be at a low temperature, right? Low energy, and or high molecular weight. So big giant molecules are going to move much slower. Okay, and so when we try to analyze this problem, the first thing I'm looking at is krypton versus argon. And so krypton generally is going to be slower. And so we have crypt because it's bigger, right? It has higher molecular weight. So krypton, negative 82 degrees. So fortunately, we have a sample here of krypton that is at the lowest temperature. So highest molecular weight, lowest temperature, that's going to be the slowest. And that's 1. Then we move on to krypton at negative 56. And I guess we can also think about the argon at negative 56 because they're the same temperature. And they're the next highest temperature after negative 82. So negative 56, we have two negative 56 temperatures. And so those are probably next, right? Because negative 82, negative 56, negative 56, as the temperature goes up, they're negative, right? So as the number gets smaller, the value gets higher. They're going up, and krypton. So krypton at negative 56 is going to be slower than argon at negative 56. Because even though the temperatures are the same, the one with the higher molecular weight, again, is going to be slower. So that's number 2. This one's probably going to be number 3. Let's think about, but let's compare it to the other one. The other one is negative 30, so higher temperature, light gas. So that's the high temperature light gas. That's going to move the fastest. That's number 4. What did we not use? We did not use the amount, the number of moles. MOL, moles, not molecular weight, not molar mass. Moles. Moles is something that we don't find in this formula, so we don't use it. What's atmosphere's pressure? Again, we don't find it in the formula for speed. We don't use it. We use the temperature, and we use the identity of the elements, which gives us the molar mass. Okay, in this question, we see a graph of speed versus probability. So probability really means just like if you have a sample of gas molecules, how many of them are going to be at this speed, how many of them are going to be at this speed, how many of them are going to be at this speed, right? And as you can see, there's a peak, right? The peak is the average, that is a measure of the average speed, but some of them are really slow, some of them are really fast. And so here's a graph. It says it models the probability of an atom moving at a particular speed for xenon gas XD at minus 3 degrees Celsius. And the question is, well, answer these questions. What is the most likely speed of a xenon atom? So the most likely speed is going to be the speed at the peak. And so we just kind of read down, and it's about 175, 180 meters per second. And Alex will give you a little range that you can fall in, because of course it's not right on the line. You have to estimate. What higher speed is only half as likely as the most likely speed? So the most likely speed is up here. That's 1, 2, 3, 4. Oh, no, sorry. Half as likely, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 lines here. That's the most likely. Half is 10 is 5, so we count 1, 2, 3, 4, 5 lines, and we read across. There's two speeds, one here, and it's asking for the higher one, so it's over here, right? And I think we're here, right? So we drop down, and it looks like it's about 300 meters per second. And then it says what higher speed is only 10% as likely as the most likely speed. So the most likely speed, again, is 10 units high. 10% of 10 is 1, so 1 unit, and it's asking for the higher speed, and so it goes out here, and that drops down to about 400. It'll be 400 meters per second. And so Alex may ask you for the higher one, it may ask you for the lower one. You've got to be careful. This question asks both for higher. It might ask you for different percents, but if it's out of 10, right, then 100% is 10 units, 90% is 9 units, 80% is 8 units, and so on. Okay, so this is one of the classic Alex slider questions. This predicts how molecular speed distribution changes with temperature and molar mass. And so this kind of combines the last two slides. The last slide we looked at the distribution, right, the distribution of speeds. 2 slides ago, we looked at how speed distributes or changes with temperature and molar mass. Okay, so here we have two questions in one. Right, the first slider has to do with this first box here. The second slider has to do with this box here. So we'll look at this one first. It says consider the following samples of gases, A, B, and C. Select a set of graphs below that shows the distribution of speeds of the atoms in each sample. Okay, so before we look at the distributions, let's think about what it's asking. It's asking what's the slowest and what's the fastest and which one is in the middle out of these three. And so what do we not care about? We don't care about, again, the amount. We don't care about the pressure, because speed, again, is U equals, this is a speed, U equals square root of 3 RT over molecular weight. So we're looking at T and molecular weight. So what do we care about? We care about the type of atom, because that gives us the molecular weight, and it's all the same. So in this side, molecular weight doesn't change. What changes? It's temperature. And so as temperature increases, the speed increases. Okay, and so temperature increases, speed increases. The slowest one is going to be the lowest temperature. The fastest one next is going to be the next highest temperature, and the fastest is going to be the highest temperature. And when you move the slider, this is the answer that you get, right? C is the slowest, right? The lowest speed. C is the lowest speed. Let's erase this, right? C is the lowest speed. And then B is the next highest, number 2, and A is the highest. Okay, so now when we look at the second group, we find that the temperature is all the same. So the temperature doesn't change. What changes? What changes is the composition. Right? And so as the molecular weight goes, how do we get an increase? Whoops. How do we get an increase in U? U goes up when molar mass goes down. So the highest molar mass will have the smallest speed. The lowest molar mass will have the biggest speed, or the highest speed. And so we need to look at our periodic table to find the molar masses. Helium is at the top, argon is in the middle, xenon is at the bottom, all noble gases. And so the biggest one is argon. That will have the slowest speed. Nope, the biggest one is xenon. That will have the slowest speed. The next biggest is argon. That will have the second slowest speed. And the lightest is helium. That will have the fastest speed. And so when we go to the slider, we'll pick this one, right? So E is the slowest, then D, then F. What you'll notice, though, if you go through get this particular problem and you go through all the sliders, you'll find another one that looks like this, right? That has E the slowest, then D, then F. Why is this one not correct? Well, this one is not correct because we need to know that as the distribution gets faster, right? As the distribution moves this way, or as the highest speed moves this way, right? The highest speed moves to the right. The distribution gets wider and shorter, right? So very slow distributions are tall and narrow, and fast distributions are short and wide, and right. So that's why this one is not correct. Okay, in this slide, we're going to continue to think about speed, the speed of molecules, but we're going to introduce a couple of terms. One of them is effusion, and the other is a related word called diffusion. And so diffusion is the word that you may have heard of before. Diffusion is very roughly the movement or spread of molecules or atoms through space. And usually we're thinking about through three-dimensional space. All right, so if I release a sample of gas all the way over here, it's going to spread through the whole room. All right, that's why if there's a student sitting next to you, that student, accidentally passes some gas, that foul-smelling gas is going to start from where it was released and spread in 3 dimensions through the room until everybody gets to enjoy or suffer from the smell. So diffusion is related, or the rate at which gases diffuse is related to this, right? Related to speed equals 3RT over molecular weight. We're not going to think about T right now, but although as T goes up, the rate of effusion goes up. What about molecular weight? Molecular weight is in the denominator, right? It's in the basement. So as the molecular weight goes up, the speed goes down, and so therefore the rate of diffusion goes down, right? As molecular weight goes up, the rate of diffusion goes down. And as temperature goes up, the rate of diffusion goes up. Now we're not going to do calculations with diffusion. However, the second term that I mentioned is called effusion, right? And we will do calculations with effusion. So I'm going to erase all this stuff with diffusion, and then now we're going to look at effusion. And effusion is also related to the spread of molecules, gas molecules, but not through space. So effusion is if you have a little tiny hole, and a little tiny hole, and some gas molecules over on this side, and they are going to spread through that hole. And so some of them are going to bounce off, right? Some of them are going to go the other way, but eventually some of them are going to go through the hole. Right? And so the rate of the spread, or the spread of the gas molecules through that hole is called effusion. And that's also related to U equals 3RT over molecular weight. So far we haven't done any calculations with this. What we're going to do now is the closest thing to a calculation that we're going to do with the speed formula, the average molecular speed formula. And so speed, the same principles apply, right? The higher the temperature, the faster the rate of effusion, and the higher the molecular weight, the slower the rate of effusion. But now it's quantifiable. And so we're going to say that, and we don't calculate rates really from nothing. We don't solve this equation, but what we do is we do comparisons, right? And we say, okay, a small gas is going to move faster than a big gas, right? Small gas molecules move faster than big gas molecules, and therefore small gas molecules will effuse faster than big gas molecules. And so what we get, and I'm not going to do the derivation. If you're mathematically inclined, you might be able to see it. You can look it up. So the rate of effusion of gas 1 over the rate of effusion of gas 2 equals the square root of the molecular weight of 2 over the square root of the molecular weight of 1. This is a formula that we need to know, and it's called Graham's law of effusion. So we know the rate of effusion, that's escape through a pinhole, right? Effusion. If we know the rate of one, we can figure out, and we know what the gases are, we can figure out the rate of the other. But in this case, we don't have the rate, but we have a ratio, 2.65 times as fast as N2 gas. So a gas made up of atoms, so that means it's an atomic gas, right? Not a molecular gas, an atomic gas. So like helium, hydrogen, not hydrogen, helium, neon, argon. One atom, gas made up of one atom, and it diffuses 2.65 times as fast as N2 gas. That means it's 2.65 times faster. And that means it's lighter than N2 gas because it moves faster. And so what's this 2.65? That 2.65 is this, rate 1 over rate 2. And so it's the rate of the unknown over the rate of N2 equals the square root of N2, the molecular weight of N2 over the molecular weight of the unknown. Right. And this ratio is this, 2.65. So it's 2.65 equals the square root of the molecular weight of N2 over molecular weight of the unknown. How do I solve this? I solve this by squaring both sides. When I square 2.65, let's look that up, or let's do that. I get 2.65. X squared is 7.02. 7.02. And when I square a square root, I take away the square root. So I get molecular weight of N2 over molecular weight of unknown. I happen to know the molecular weight of N2. The molecular weight of N2, you can get that from 2 times the atomic weight of N. And so I'm going to substitute that, and it's approximately 28 AMU, right? And so 28. Okay, and so what can I do? I can cross multiply, and I'm going to solve now for the molecular weight of my unknown. I'm going to erase all this. And all right, so now I'm going to solve the best way I can. Like I said, maybe I will cross multiply. So this times this equals this times this. And I get, let's see, right, 7.02 times the molecular weight. I'm just going to call it UK here, unknown, equals 28 times 1. And then I divide both sides by 7.02. And I get the molecular weight of the unknown equals 28 divided by 7.02. That's 4.0. And that's AMU, right? Because this is AMU. And okay, so the molecular weight of the unknown is 4.0. Is there an atomic gas or an element, gaseous element, that has an atomic weight of 4.0? Indeed there is. That is, if I look it up on my periodic table, helium. And so write the chemical formula of the gas, it's He. Okay, so that's about a half hour of chemistry that we just did together. There is more to go, but if you want to take a break, this would be a good time to take a break and come back in a little while, and we will keep on going. I'm going to shift gears a little bit. So if you want to clear your head, get a snack, do some exercise, now is a good time. All right then, let's keep on going. We're going to change directions here. We're going to look at gas laws. And so the main gas law, the central gas law, is PV equals nRT. Okay, this is the ideal gas law, or the ideal equation of state. P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is the temperature. Right, so P is pressure, volume, N is moles, R is the gas constant, and that value, if you remember from class, has gets different numbers depending on what unit of pressure we're using. Right, we can use atmospheres, we can use millimeters of mercury or torr, we can use pascals or kilopascals. Right? And T is temperature in terms, and the unit on the temperature is always Kelvin. We're looking at gases. Okay, and from PV equals nRT, we derive the other gas laws that we use mostly when conditions are changing. So we get P1 V1 over T1 equals P2 V2 over T2, right? And that's N is constant. When N is constant, that means basically we have one sample of gas, and that sample of gas is undergoing some changes, but nothing's being added and nothing's being taken away. If we have mixtures of gas, or gas being added or gas being taken away, we can think about Avogadro's law and partial pressures. I'm not going to review that here. You can review that in the 2015 YouTube videos if you want. From the complete gas law here, we get the other gas laws, such as P1V1 equals P2V2, Boyle's law, right? And that is constant T and assumed constant N also. We get P1 over T1 equals P2 over T2. That's constant V and constant N. Right, so that's a container that's rigid. The volume doesn't change. It can't expand or contract. In that case, what this equation is saying is that an increase in temperature leads to an increase in pressure. Now, if we have a different kind of container where the container can change volume, but the pressure doesn't change. So this is a situation such as when we're using the cylinder with a movable piston that can move up and down against a constant pressure, often atmospheric pressure, but not always. The pressure is constant, but the volume can change, and we get V1 over T1 equals V2 over T2. Okay, so we've done examples of those, and we're not going to do more examples right now. Right now, this is just like the 3-minute review. Right now, I'm going to erase all this stuff, and we're going to look at the problem. Right, the problem is, at its heart, a PV equals nRT problem with a little twist. So it asks us to find, well, it gives us a whole bunch of information. And it gives us the temperature, 130 degrees Celsius. It gives us a volume, 1,370 milliliters. Right, temperature, volume. It gives us a pressure, 1 atmosphere. The ideal gas constant we look up in a table, so we always know that. And so what we need to solve for then is moles. The question doesn't ask for moles, it asks for molar mass. Here it is, it asks for molar mass. But wait, what is molar mass? Molar mass is grams per mole of a substance. In this case, the unknown compound that's turned entirely to gas, vaporized. That substance weighs 4.31 grams. That gives us the grams here. If we can find moles, which we can from PV equals nRT, because we have P, we have V, we have R, and we have T, and find N, then we get the moles. We do grams divided by moles, and right, the grams comes from here, the moles comes from here. Then we can find the molar mass, and then often we can find out what the substance is. Okay, so let's dissect the problem a little more. When I see 130 degrees Celsius and I'm looking at gases, I need to convert that to Kelvin. Gases temperature is always Kelvin, so 130 plus 273 to go from Celsius to Kelvin, that gives me 403 Kelvin. And then volume needs to be liters, so I take my milliliters, 1,370 divided by 1,000, and I get 1.370 liters. 1 atmosphere, so that tells me because it's atmosphere, I'm going to use this particular unit of R equals 0.0826, and the unit is liters, atmospheres per over mole Kelvin. Okay, so I have all my information set up, and I know I need to solve for N. So what I'm going to do is I'm going to divide both sides by RT. The RT cancels off the right, and I get N equals PV times divided by RT. Okay, so do I have P? I have my P. P is 1.00 atmospheres. V is 1.370 liters. 370 liters. And then everything's going to equal N eventually, right? That's what I'm looking for. And then I'm writing it out this way because I want to show you something about the units, right? R is 0.0826 liter atmospheres per mole Kelvin. But it is in the denominator, so that means I'm dividing. And so if I divide, it's the same as multiplying it and putting it in the basement, right? And so I'm going to do 0.08206 liters atmospheres, and mole Kelvin goes on the top, right? Here, the unit mole Kelvin is in the bottom, liters atmospheres on the top, because I'm dividing everything, the number and the unit all gets flipped. So 0.08206 liters atmosphere per mole Kelvin, I'm dividing. And then I'm also dividing by temperature, right? So temperature, if I'm dividing, I'm putting on the bottom, it's 403 K. And when I do that, what happens to the units? Atmospheres cancels with atmospheres, liters cancels with liters, Kelvin cancels with Kelvin, and what's left is moles. Voila, right? And so I do that math, and I get, when I do that math, 1.00 times 1.370 divided by 0.08206 divided by 403. And I get N equals 0.414 moles. Almost done, right? I have moles, and so that's this part of the equation. Grams, this part of the equation comes from here, so I get the molar mass equals 4.31 grams divided by 0.414 moles, and I get, when I do that math, I get 4.31 divided by 0.414, 10.4 grams per mole. I just realized I made a mistake here. It's not 0.0404, it's 0.0414. And so this should be 0.0414. I left out a 0. So I get 0.0414 moles. And my answer is not 10.4. That's a little strange for molar mass. It's 104 grams per mole. Sorry about that. Okay, so that's PV equals nRT with a little extension on top of it, which allows us to get molar mass of a gas. Once you know the molar mass of a gas, then it narrows down quite a bit what that gas could be. Okay, so we have a whole bunch of things, right? We have grams, we have pressure, we have volume, we have temperature. There are some other things that we can get from this information. So I'm going to erase a little bit, and I'm going to erase all the work, but I'm going to leave the answers here, right? And so what we have is okay, so now I've cleared off some board space, and what we have is all the information about the sample of gas now. There's a couple of other things that we can find. We can find, for example, density of the gas. What's the density of the gas? Well, density is mass over volume, right? D equals m over v. Do I have a mass of this gas? Sure I do. It's 4.31 grams. So, and do I have a volume? Sure, I have a volume. It's this many liters or this many milliliters. So depending on how I want to represent my density, I can use either liters and get grams per liter or milliliters and get grams per milliliter. For gases, we usually use liters because gases are generally not very dense. So I'm going to do 4.31 grams divided by 1.370 liters. And when I do that, I get the density equals 4.31 divided by 1.370, 3.15 grams per liter. Another thing that I can find is the molar concentration of the gas. Now, molar concentration is a concept that we learned in when we're talking about solutions, but molarity, what is molarity? Molarity, capital M, is moles per liter. Do we have moles? Sure, we calculated moles. That was the point of the PV equals nRT. We got moles, and we have the same number of liters. So the molarity equals 0.0414 moles divided by 1.370 liters, and I get 0.0414 divided by 1.370, and that equals 0.0302 molar or moles per liter. Okay, so all these things kind of work together, and you can work all these things in any direction. If you understand your units, or if you understand what's happening to the gas, or what the gas looks like, feels like, what the molecules are doing, then there's many different ways to set up problems, but usually you should be able to unravel it. Okay, so this is the same problem here. I just cleared the board. There is a formula. I'm not going to derive it here. If you're inclined, you can try to do it. But the formula is that relates all those items that I talked about. Is molar mass, or molecular weight, if you will, equals density times R times T over P. Or, because what's density? Density is mass over volume, grams, often grams per liter, right? I mean, in this case, it's going to be grams per liter. Molar mass also equals mass in grams times R times T over PV. So both of these equations are equations that you can use now that you understand kind of the process of how we go through and get them. Okay, finally we can put this all together, right? And connect what we've been doing with stoichiometry and chemical reactions. And so remember I told you what's at the middle of our table, or our flow chart. The middle of our flow chart, a reaction flow chart, or a counting flow chart really, is moles. And moles is really just a way of counting molecules. And molecules are the individual things, the individual items that are going in and reacting with each other. They're colliding with each other, they're breaking bonds, they're forming bonds. And as they're doing that, they're changing from one compound to another compound, or from free elements, free atoms, into molecules. Right? And so think about that story. Think about those interactions. What's changing into what, and how those atoms and molecules are rearranging. Okay, so we know how to get from moles to atoms or molecules Sometimes we call those particles, right? We know how to convert between those guys. We convert between those guys using Avogadro's number, 6.022 times 10 to the 23rd, and sometimes use a unit inverse moles, 1 over moles. It's per moles, atoms per mole, molecules per mole. We don't use that a lot in our calculations, but that's the basis of everything, right? We're counting molecules. Very often we use moles to mass and grams, and the way we interconvert between mass and moles and mass is the molar mass, right, which has units of grams per mole. You get that from the periodic table. You look it up. You look up the atomic weights or the atomic masses. You add them all together. You get the molar mass, right? Grams per mole. When we're looking at solutions, we have, and actually now, now that we've done the last slide, we can sometimes do this with gases also. And we have concentration, and if we have a concentration, we use the volume to get back to moles, and if we have a volume, we use the concentration, molar concentration, to get back to moles. Now we have one more way to get to moles, right? And that way is what? It's PV over RT equals N, right? So if we have pressure and temperature, we use volume to get N. If we have pressure and volume, we use temperature to get N. And with volume and temperature, we use pressure to get N. And N is moles, right? So we have now several ways to get us into moles. Once we have moles and we have a balanced chemical equation, we can use the coefficients in the balanced chemical equation, right? Coefficients, or the coefficient ratio, and sometimes that's called the mole ratio, right? To get us from moles of A to moles of B. And once we get from moles of A to moles of B, oh, that is really ugly. I'm going to rewrite it. Once I get from moles of A to moles of B, I can use the molar mass of B to get me the mass of B, right? Let's say A is a reactant and B is a product. If I have, it's a gaseous reactant, I can use PV equals nRT to get me moles of A, use the coefficient ratio to get me moles of B, use the molar mass, get me mass in grams of B, right? And then I can also do these other things here, right? So if I can find concentration. If I have volume, I can find volume. If I have concentration in molar, right? Concentration in molar. Or I can use PV equals nRT, right? Once I have moles, to find pressure if I have V or T, or volume if I have P or T, and so on. And again, I can also go back and find atoms, molecules, particles, but generally we don't do that very much in stoichiometry. Okay, so we're building out our chart even more. Next slide, we're going to use some of this chart. Okay, so here's the last problem we're going to work today. It says combustion of hydrocarbons, such as butane, produces carbon dioxide, and then it gives you a story about greenhouse gases. And then we're going to skip over this, come back to it, and it says, suppose this amount of butane is burned in air, oxygen, right, at a pressure of exactly 1 atm, atmospheric pressure, at a temperature of 16.0 degrees Celsius. Calculate the volume of carbon dioxide gas that is produced. Be sure your answer has the correct number of significant digits. Okay, so this is using a mass of butane, and that's going to give us some product, carbon dioxide, and that product is a gas, and that has a pressure and a temperature. So if I have pressure, temperature, what can I find? I can find, well, I need moles from the grams and from the coefficients. So if I have moles, pressure, temperature, what can I find? That's right, I can find volume. Okay, so before I do any math, what I need is a balanced chemical equation. And so what this question is assuming is that this is what's called a complete combustion. The only products are carbon dioxide and oxygen. And we've seen a bunch of, reactions, including on your last exam, that had this general format, right? Something plus oxygen gives us CO2 plus O2, plus H2O. So in this case, we're given C4H10. In order for it to burn, it has to be gas. And then a combustion reaction is a fuel combines with oxygen. And the oxygen gas, and the products are CO2 gas and H2O, and the water here is also in the gaseous state in general. At least it starts that way. Okay, so we have our equation here, and we know the butane is a gas. It asks for states, right? We know the butane is a gas because it says gaseous butane. Oxygen is always gas, and the products are gaseous carbon dioxide and gaseous water. Now we need to balance, right? And so I'm going to start by putting a 2 here, and nope, I'm going to start by changing that 2 to a 4, and I have 4C on both sides. And then I'm going to put a 5 here to balance my hydrogens. And now I have 8 plus 5 is 13. So 6.5, 13 over 2 oxygen. Now, if you pause this and you count everything up, you'll see that should work, but I don't really like that because I don't like to have the 2, the over 2, right? So I'm going to double everything. This one becomes a 2. This 13 over 2 becomes a 13. Whoops. Becomes a 13. Becomes a 13. This 4 becomes an 8. And this 5 doubles and becomes a 10. Right. Okay. That's an ugly 10. I'm going to fix it. 10. All right, so that's balanced, I think, right? We've got 8 carbon on both sides. We've got 20 hydrogens on both sides. And we've got 26 oxygens on both sides. Yes, we do. Okay. And so that's this part. And the second part is kind of the new part, right? So we have 0.380 kilograms. We multiply by 1,000 to get 380 grams, right? Because when we're dealing with molar masses, which according to the chart on the last slide, we're probably going to have to use, it's grams per mole. And so suppose 380 grams of butane are burned in air. The air, this implies oxygen, and it's probably going to be excess, right, because it doesn't tell us how much. At a pressure of 1 atmosphere and a temperature of 16, what happens when we see temperature in gases? We have to add 273, and that gives us 289 Kelvin. And we have to convert to Kelvin. So find the volume. Okay, so this smells to me like a PV equals nRT problem. Pressure, we've got, this is where we're looking for the product, right? Carbon dioxide. The pressure we've got, it's 1 atmosphere. The volume we're trying to find. Temperature we've got, R we always have. We need moles. How do we get moles? Well, we have to think back to our chart. I have mass of butane, that's A, mass C4H10. I'm going to go to moles of C4H10. Right now, that's using the molar mass of butane. And then I'm going to go to moles of CO2 using the coefficient ratio. Right? 2 C4H10 and 8 CO2. That's the coefficients or the mole ratio. And then once I have moles of CO2, I'm going to use now V equals nRT over P to get my volume. Okay, so what do? I need the molar mass of C4H10. At this point, you need to calculate the molar mass of butane. I'm going to cheat and look it up. Molar mass of butane. The molar mass of butane is 58.12 grams per mole. So 58.12 grams per mole. Okay, so what am I going to do? I'm going to take the mass of butane, the mass, not the molar mass. I'm going to start with the mass, which is 380 grams. 380 grams of butane. And I'm going to use the molar mass of butane, divide 58.12 grams per mole. And this is all butane, right? And I'm just going to call it BU for now. And that gives me 380 divided by 58.12. That gives me 6.54 moles of butane. Then, that's the C4H10, right? This is butane. Then I'm going to, so that got me from here to here. Now I'm going to use the coefficients like I learned how to do in chapter 3 and get from moles of butane to moles of CO2. Right? So for every 2 butane, I use 8 CO2. The way I like to think about it is I take the moles of what I have. Right? Remember, this is the butane. And then what I want is 8 the CO2, so I do the 8. What I have is the 2 butane, so I do 1 over half, and I get 6.54 times 8 divided by 2. That gives me 26.2 moles of CO2. Okay, so the last thing I need to do is go from here, moles of CO2, to volume of CO2. So I do V equals nRT over P, right? I've divided both sides of the ideal gas law by P, and I got V equals nRT over P. And I plug in, right? And I plug in N for my moles, and R, I'm still going to use 0.08206 because it's atmospheres. My temperature, and divide it by my pressure, which is 1, and I'm going to get my volume. All right. Okay, so I'm going to erase my work down here because I'm out of space, obviously. And I'm doing V equals nRT over P. And so V equals 26.2 moles. That's what I just erased, times R. And I mentioned in class, if you do this without units, I'm not going to be mad, just because it's often really hard to keep track of writing everything down. So R is 0.08206 when my pressure is here in atmospheres. Right? If pressure is something else, you have to look up the other R. T is 289 K, and P is 1. Right? And so I do that, and I get 26.2 times 0.08206 times 289 divided by 1, and get the volume equals 621 liters of CO2. All right, and that's a lot of CO2, right? So that this is saying the point of this question is about greenhouse gases, and so this is saying yes, we produce a lot of greenhouse gas. All right. There's a lot more that we could do with this problem. And so if you followed thus far, then you can think about how you might want to do the following. Right? How could you find the mass of CO2 produced? Could you find the density of CO2 produced? And or the concentration of CO2 produced. Right. These are three things that you could think about. And if you have answers that you'd like to check, then email me, and we'll see if you're right. All right, that is the end of this talk on gases, and this is the end of our chapter on gases. Well, enjoy your spring break, and we will see you in a week or so. Take care.